Why do balloons stretch when they inflate instead of pop? What makes an aluminium wheel strong enough to support a car that's 60 times its own weight? How does a paper aeroplane turn into a paper envelope? And what makes a whistle whistle? Find out next on How Stuff's Made. Balloons don't actually grow on trees, but they do come from them. That's because balloons couldn't be made without the milky sap of rubber trees, which we know as latex. Latex is a naturally stretchy substance, but it's not until the latex is turned into rubber that the balloon has the elasticity it needs to inflate to 5 times its original size. Balloons start out in liquid form, with the milky white latex from the rubber tree. Powdered pigment changes the colour of the latex. And to enhance its natural stretchiness, other elements, including sulphur and zinc oxide, are added to the mix. They'll be activated later when the mix is heated to turn the latex into rubber. These rows of ceramic shapes that look like little light bulbs are actually the moulds that will form the latex into balloons. The moulds are washed in a tank of citric acid to burn off any impurities. Even the tiniest speck of dust on one of them could cause a flaw or weakness in the balloon. In order to make the latex stick to the moulds just enough, but not too much, they are coated in calcium nitrate. The calcium nitrate is a coagulant that helps the latex stick to the forms. An oven dries off the water, leaving only a film of calcium nitrate on the moulds. Finally, the vat of blue liquid latex rises up to completely coat the moulds, forming the skin of the balloon. An oven heats the balloons for 5 minutes to firm up the skins even more. Then 2 nylon brushes roll down the top of the warm skin, which is still soft enough to curl into the lip that's used to blow the balloon up. But it's not until the balloons bake in an oven at 80 degrees that the skin is transformed into the stretchy rubber of a balloon. The heat activates the sulphur and zinc oxide in the latex mix, which strengthens the bond between the molecules in the latex, converting it into rubber. And it's because of that super strong bond between the molecules that rubber is so rubbery and stretchy enough to inflate into a balloon without tearing. Once the rubber is set, a squirt of water between the ceramic moulds and the balloon loosens the skins. So a set of pads that are covered in carpet can strip the balloons off the moulds 1 row at a time. A few balloons in every batch go through a series of spot tests to check for weak spots, lumps and tears. Then some balloons get a custom paint job, which must be done while they are inflated. Suction cups rotate the balloons as they pass through a series of silk screens until all sides are printed. Then wiper blades apply a thin layer of quick-drying rubber over the ink. And a ride through a heat tunnel dries everything in place. The balloons deflate and sprayers coat the finished items in a solution of water and silicone, which gives them a glossy finish and prevents them from sticking together in the bag. Now these little rubber pouches of joy are ready to stretch themselves and blow up at a birthday party or other celebration without popping. And that makes the party and the world a less uncheery sort of place. The rubber may be what hits the road, but it's the wheels that are doing most of the work. While the tyres fit around the wheels to cushion the ride, it's actually the wheels that bolt to the axle of the car and turn to make the car go. Each wheel has to be light enough for the car to perform well and get good fuel efficiency, but also strong enough to support the weight of the car, which can be 1,800 kilos or more. The safety of the whole car and everyone in it is riding on it, so the wheel cannot fail. To make the wheels as strong as possible, each one is machined from a single piece of aluminium. That way, there are no parts to come loose or break. It takes a carbide blade to cut the raw aluminium stock into 14-kilo billets. Each billet makes one wheel, with 20 billets cut from each bar. The billets travel through an oven for 2 hours until they're heated to almost 500 degrees Celsius. This softens the aluminium for forging without melting it. A rotary forge machine takes this softened billet and presses it into a thin disc using 3,600 tons of pressure. This incredible pressure, along with the heat from the furnace, not only reshapes the aluminium, it also rearranges the actual molecules into a tight circular pattern. This new molecular arrangement gives the wheel its strength and durability. When the disc is cooled to room temperature, it travels to the cold forming machine. The disc sits on a mandrel. Then giant rollers drop down and, like in some sort of monstrous pottery, the rollers mould and stretch the aluminium into a wheel. A coolant cuts down on the friction but blocks the process from view. We asked them to run the machine without coolant for a minute to see how it shapes and stretches the metal. The aluminium goes from a flat disc to a wheel that's 45 centimetres tall in just 45 seconds. A rack hoists the wheels up into a furnace that heats them to 530 degrees. Once again, the aluminium is not melted. It's only heated or tempered to even out and further strengthen its molecular structure. A tank of cold water rolls into place under the furnace to immediately cool the wheels as they emerge. This literally freezes the new denser molecular structure in place, locking in the strength. A computer-controlled blade carves out the rims and other contours of the wheel. A smaller mill creates a spoke-like design, which is part style and part function. In addition to making the wheels look snazzy, the openings help air circulate and cool the brakes. The mill cuts away more material to create holes for the lug nuts that hold the wheel to the axle. The finished wheel is carefully inspected to make sure it's perfectly round. A dial takes measurements at various angles. If it's not perfect, the tyre could wear out faster in certain spots, creating a safety hazard. If the wheel passes the test, buffers move in to polish the aluminium to a bright shine. And the brand new wheels are ready to roll. Next, find out what really happens inside a whistle. And discover the secret to folding 800 envelopes every minute. This type of envelope, sometimes called the number 10, is one of the most widely used envelopes in the world. That's because its dimensions, roughly 9.5 by 24 centimetres, are perfect for folded sheets of A4 paper, which is a standard size in the UK and Europe. But unfold one and you'll see the dimensions of this common envelope are not what they seem. The envelope is actually made from a single sheet of paper that unfolds into a triangle with rounded edges. It looks more like a paper aeroplane than it does an envelope. Just a single roll of paper stock like this produces 45,000 envelopes. And when fed into this webbing machine, 10 rolls or 70 kilometres of paper can be cut at once. The webbing machine gathers the paper from all 10 spools and feeds it as a single stack into the die cutter. A die, or a template, like this waits inside the machine. Recognise the shape? Hydraulic pressure forces the paper through the sharp edges of the die, cutting through all 10 sheets at once for maximum efficiency. The sheer force of the die presses out 20 envelope blanks at a time, and up to 3 million a day. As the freshly cut envelope blanks emerge from the die cutter, a robotic arm grabs them and stacks them on pallets. Each stack contains exactly 3,000 envelopes and weighs 20 kilos. After the robot fills a pallet, the envelope blanks move on to the real multitasker of the operation: the rotary adjustable machine. This amazing machine can process, fold and glue 36,000 of these envelopes every hour. The envelope blanks feed into the centre of the machine, where a die cuts out the address window and then adds clear film to cover it. Next, the machine stacks the envelopes in such a way that only their licking flaps are exposed. That way, when the envelopes pass by these sticky rollers, the non-toxic licking adhesive ends up on the flaps and nowhere else. The envelopes then dip down to a conveyor belt inside the machine and pass through a dryer. A fraction of a second later, the envelopes emerge on the other side of the machine for folding. The machine forces the envelope blanks through 2 silver guardrails to fold in the sides. We've slowed it down so you can see the folding action. At real speed, this machine completes 600 to 800 side folds every minute. Next, the machine applies a strong, permanent glue so rollers can fold and seal the bottom flap. At regular speed, it powers out 10 to 13 envelopes every second. Small spinning sensors count out 500 folded envelopes per box. And the envelopes are ready, unless the order calls for custom printing. In that case, a 4-colour offset printer adds the return address and business logo. As the 4 colours are layered on, the logo emerges. The ink is made from vegetable oil, so it's completely biodegradable. A blue ultraviolet light instantly dries the ink, enabling the machine to spit out 30,000 printed envelopes every hour without a single smudge. Ever wondered what makes a whistle whistle? It comes down to 3 things: the puff of air that's blown into the whistle, the pea inside the barrel, and the slot on top of the mouthpiece. The air travels up the mouthpiece until the sharp edge of the slot slices it in two. The top of the air current peels away from the slot, generating sound waves above the whistle, while the bottom part flows into the barrel, where it swirls around the curved walls, taking the pea with it. It is then released back out of the slot to amplify the sound waves above. The tumbling pea disrupts the airflow, giving the whistle its distinctive warble. But surprisingly, the pea doesn't go in until the entire whistle is assembled. Like many musical instruments, these whistles get their sound from high-grade brass. That's because this type of brass is easily shaped, and it vibrates in such a way that creates a high-pitched sound. A brass coil feeds into a 35-ton press that punches out forms that look like a square with mouse ears. This becomes the top part of the whistle. The tops stack into another press that folds down the ears to make the sides of the whistle barrel. At the same time, the press stamps out a dimple onto the mouthpiece, something for the lips to grip when the whistle is blown. To make the bottom of the whistle, another coil of brass feeds into a press that does double duty. First, the press cuts notches that will lock the bottom to the top of the whistle. And second, it begins rounding the bottom piece. The whistle bottoms stack in another machine that uses 18 tons of pressure to curl the brass into a fully rounded barrel. The barrel is a resonant chamber where swirling vortices of air generate sound waves that rattle the pea and force a trilling sound out of the top. The barrel must be perfectly round, within a fraction of a millimetre, or it won't align with the top and the whistle won't work. The top and bottom pieces snap together, and the space between the barrel and the top of the mouthpiece forms the slot that slits the air current to create the whistle sound. A conveyor takes the whistles to a rotating soldering table. A robot places a tip that will attach to a keychain in a soldering pocket. A dab of solder squirts onto the tip. Then a robotic arm attaches a whistle. solder is injected inside the whistle to fill the seams. But it takes a hot flame that shoots through the whistle to melt the solder. A blast of cold air instantly solidifies it. Then, for the polish, the whistles are dumped into a giant washer containing 220 kilos of hard plastic pellets. As the machine vibrates, the pellets act like sandpaper and use soapy water to scrub off excess solder while smoothing and buffing the edges. In 10 hours, this tumbler can clean and shine 4,000 whistles. And it's not until the whistles are fully polished that the peas go inside. The peas, which are made of synthetic cork, are loaded into a machine that forces them through the vent and into the whistle. We have removed the side of the whistle to reveal how the pea is squeezed so it will fit through the vent. Once inside, the pea bounces back into shape, so it can never fall out. And unlike natural cork, synthetic cork doesn't absorb moisture, crumble or clog the whistle up. So this whistle will produce a sound that can be heard up to 800 meters away whenever it's blown.